This research paper introduces a new method called Bayesian dynamic borrowing, or BDB, to improve the detection of adverse events in pharmacovigilance. The authors, from GlaxoSmithKline and the London School of Hygiene and Tropical Medicine, focus on analyzing data from the FDA Adverse Event Reporting System, known as FAERS. Their approach enhances traditional disproportionality analysis by incorporating semantic similarity between medical terms. At its core, the method uses a Bayesian hierarchical model with a meta-analytic predictive prior. This allows for dynamic borrowing of information from related adverse event terms in the MedDRA system, which is a standardized dictionary for medical terminology. Specifically, they weigh the borrowing based on semantic similarity measures, or SSMs, so that terms that are clinically similar to the target adverse event can contribute more reliably to the analysis. This helps overcome the limitations of rigid grouping in standard methods, where adverse events are treated independently without considering their underlying connections. The paper evaluates this new approach, termed IC SSM, using FAERS data from 2015 to 2019. They compare it against the traditional information component, or IC, analysis and a version that borrows information at the MedDRA high-level group term level. To assess performance, they created a novel reference set called PVLens, based on FDA product label updates. This set helps evaluate how well the methods identify adverse events before they are officially labeled. In their results, IC SSM showed improved sensitivity, meaning it detected more true positive signals compared to the traditional IC and the high-level group borrowing method. For instance, it identified more adverse events accurately and detected signals up to 5 months earlier. However, there were minor trade-offs, such as slightly lower F1 scores and Udin's index overall. Despite this, IC SSM performed better in the early post-marketing period, providing more stable and relevant estimates. The authors explain that spontaneous reporting systems like FAERS are crucial for post-marketing safety surveillance of medicines and vaccines. These systems help identify emerging safety concerns that might not have been detected during clinical trials. Individual case safety reports, or ICSRs, form the backbone of this process, allowing for the detection of new safety signals through quantitative analysis. Historically, quantitative signal detection began in the late 1960s and 1970s, but it became routine in the 1990s due to increased data availability and computational power. The most common methods today rely on 2x2 contingency tables to calculate disproportionality scores, like the information component. These scores help flag potential safety issues by comparing the observed frequency of a drug event pair against what's expected by chance. However, these traditional methods have limitations. The data in spontaneous reports can be noisy, with issues like underreporting or missing information. Moreover, they treat each adverse event term independently, which doesn't account for clinically similar events that might share the same underlying biological mechanism. The authors argue that this is where their Bayesian dynamic borrowing comes in, as it clusters related events more effectively using semantic similarity. To break this down, semantic similarity measures involve comparing the meanings of medical terms. For example, in MedDRA, preferred terms like headache and migraine might be similar because they both relate to neurological symptoms. The BDB approach uses these similarities to create a weighted borrowing system, where more similar terms contribute more data to the analysis. This makes the detection process more context-aware and scalable. In the study, the authors applied this to real-world FAERS data. They found that IC SSM not only boosted sensitivity but also offered advantages in stability, especially early after a drug's market release. This is important because early detection can lead to faster interventions, potentially preventing harm to patients. The paper also touches on the broader context of pharmacovigilance. While some methods incorporate external data like sales or prescription volumes, the ones based solely on ICSR data are more practical for timely signal detection. The authors note that even though more complex techniques have been proposed, they haven't always outperformed the basics. A key insight from the EMI-Protect project is that performance often depends more on the detection threshold than the algorithm itself. Looking at the results in more detail, IC SSM consistently picked up more true positives and provided earlier warnings. For instance, in their analysis, it outperformed the other methods in identifying adverse events that later appeared in FDA labels. The trade-offs in metrics like Uden's index, which balances sensitivity and specificity, were minimal and didn't outweigh the benefits, particularly in the initial months post-launch. The authors emphasize that this approach is a scalable enhancement to existing disproportionality analysis. By using semantic similarity, it addresses the noise and independence issues in traditional methods, making it a promising tool for drug safety monitoring. Finally, the paper suggests future research directions. They recommend validating this method with other datasets beyond FAERS and exploring additional similarity metrics or Bayesian inference strategies, possibly using more detailed case-level data. The keywords highlight the key areas: pharmacovigilance, semantic similarity, Bayesian borrowing, signal detection, and drug safety. This method represents a step forward in making pharmacovigilance more efficient and accurate, ultimately helping to ensure that medicines on the market maintain a favorable benefit-risk profile.